Hello, my name is James, and I am going to be presenting the past paper 5.2 from May-June 2021 with my friends Rebecca, Kenneth, and Calista. I'll be doing number 1 and 2. For number 1, an ordinary fair die is thrown repeatedly until a 5 is obtained. The number of throws taken is denoted by the random variable x. Write down the mean of x. The mean of x is 6. Since this is a geometrical function, the probability of getting a 5 from a ordinary fair die is 1 over 6, since it's fair. There are 6 sides of the die. But the mean of a geometrical function is 1 over the probability, so it is 1 over 6, which means it's just 6. Find the probability that a 5 is obtained after the 3rd throw, but before the 8th throw. So the probability of 5 is still 1 over 6. However, we want to get it after the 3rd throw, meaning every situation, the 3rd throw has to be all first from throw 1 until 3. We should not get a 5, but we should get a 5 at throw 4, 5, 6, or 7, either one of them. Meaning if we get it on 5, 4 will not be counted, which also applies for the rest of the numbers. However, it says before the 8th throw, so we can only go until the 7th throw, and we do not include the 8th. So the probability to not get a 5 on the first throw will be 5 over 6. Same with the second, 5 over 6, and third, 5 over 6. However, on the 4th, it will be 1 over 6, since we want to get a 5. This will be applied for every number. So this one will be 5 over 6, 5 over 6, repeating here, everywhere, except for the 5th, 6th, and 7th throws, which is 1 over 6, 1 over 6, and 1 over 6. So you would multiply the probabilities for each possible case. This one being throws 1, 2, and 3, and the 4th throw, 1, 2, 3, 4, and 5, repeating until 1, 2, 3, 4, 5, 6, and the 7th throw. You would add all the probabilities, and it would equate to 0.2996, which is roughly equal to 0.300 with 3 significant fingers. C. Find the probability that a 5 is obtained in fewer than 10 throws. This is pretty much the same as B, but extended. So on the first throw, we want to get a 5, so the probability will be 1 over 6. On the second, we want to get a 5 on the second, so not on the first. It will be 5 over 6 times 1 over 6, and you can repeat that until you get 9 throws, which is fewer than 10. So 1, 2, 3, 4, 5, 6, 7, 8. All of this, we do not want to get a 5, but on the 9th throw we want to. So 1 over 6 being the first throw, this being the second and first throw, first, second, and third, until not first. This is the first, this is the second and first, this is the third, this is the first and second, this is the 9th throw, and this will be 1 until 8. If you add all of the probabilities like in B, your result will be 0.806. On to number 2. The weights of bags of sugar are normally distributed with mean 1.04 kilograms and standard deviation sigma kilograms in a random sample of 2,000 bags of sugar. 72 weighed more than 1.1 kilograms. Find the value of sigma, or standard deviation. So this is a normal distribution, so we will use normal distribution. The mean is 1.04 kilograms, which is here. The standard deviation, or in this case variance, which has to be written down, is sigma kilograms. So the probability of x being larger than 1.1 kilograms would be in the regular formula, which is probability of z larger than x minus mean over the standard deviation, which Oh, that looks like a 6, but that's sigma. However, Z also is the equivalent to 72 weighing 72 out of 2000, which the probability is 0.03636, and on a normal distribution graph, 0.036 is this small area on the left side, but we cannot calculate that, so we would move it to the other side, and this entire area would be 1 minus 0.036, which equals to 0.964. And on our normal distribution function table, negative z, since it's moved to the other side, that's why it's negative, 0.964 is 1.799 or 1.8. It's pretty much the same thing, and I will go with 1.8 since it is simpler to count with. So z is equal to negative 1.8, since before it's negative z. Negative 1.8 equals to this, which is taken from this, because they're the same thing. Negative 1.8 equals to 1.1 minus 1.04 over sigma. And so that means sigma equals to 1.1 minus 1.04 over negative 1.8. That equals to negative 0.03 repeating, which is the same as negative 0.0334, 3 significant figures. And since this is in kilograms, the unit is in kilograms, we cannot have the value become negative.
Hi, my name is Kenneth, and I'll be doing questions 3 and questions 4 for the May-June past paper. So it says that in question 3 that on each day that Alexa goes to work, the probabilities that she travels by bus and by train and by car are 0.4, 0.35, and 0.25 respectively. It should look like this. So let's start with here. This is the bus. She states that it's 0.4 by train. It's 0.35 here, and by car it's 0.25. Now it also states that when she travels by bus, the probability that she arrives late is 0.55. So let's draw our branch here. So if she is late, I'll label as L, is 0.55 here, and not late will be 0.45 here, right? It states that when she travels by train, the probability that she arrives late is 0.7, so our branch here. So late equals to 0.7. That means not late equals to 0.3, which is 1 minus 0.7. By car, it states that the probability that she arrives late is x, so we'll just write here. Late equals to x, and for not late, that would lead to 1 minus x. Right. So on the question, it says that on a randomly chosen day when Alexa goes to work, the probability that she does not arrive late is 0.48. So that would mean that not late equals to 0.48. That's out of the total. And so not late equals to equal to bus and not late, train and not late, and car and not late. Okay, and that would all equal to sum of 0.48. That would equals to 0.48, 0.4 times 0.45 bracket plus 0.35 times 0.3 bracket plus 0.25. That was 1 minus x. That's because it's above x here. Now all equals to 0.48. Right, so we would go here, so that would lead to 0.18 plus 0.105 plus 0.25 minus 0.25x here. And now it equals to ultimately 0.48, right? And then that means that if we add this up and we move it to the right side, we would get 0.25x equals to 0.055. And then if we just divide this to here and we switch there, we will get that x equals to 0.22. So the probability that she does not arrive, the probability that she arrives by car and she is late is equals to 0.20. So for section B, question 3, find the probability that Alexa travels to work by train given that she arrives late. So probability that arrives by train and arrives late. And this equation equals to P, train intercept L, over probability of lateness. So in the last question we get that not late equals to 0.48, so late would be 0.52. Yes. So to find the probability of train and arrives late, we get 0.35 times 0.7 over 0.52, and we will get the final answer 49 over 104. Next, I'll be answering question 4a. A fair spinner has sides number 1, 2, 2. Another fair spinner has sides number -2, 0, and 1. Each spinner is spun. The number of sides on which a spinner comes to rest is noted. The random variable x is the sum of the numbers for the two spinners. A. Draw the probability distribution for x. Okay, first we need to find all of the possible outcomes. Let's draw here. -2, 0, 1, 1, 2, 2. So that's this. Right, so the sum of these is -1. Sum of this, 1. Sum of this, 2. Sum of these, 0. Sum of these also 0. This, 2, and 2. And finally, 3 and 3. Right. So after we get all the possible outcomes, we get to finally draw the graph, the distribution table. So draw here. This would be x, and this is p, right? So -1, 0, 1, 2, and 3. So for -1 we get 1 over 9. For 0 we have 2 over 9. For 1 we have 1 over 9. For 2 we have 3 over 9, or 1 over 3. And finally we have 3, the probability of 2 over 9. So finally for question 4b, find EX or expectation for x and variance for x. So expectation of x. So we start with 1 times 1 over 9 plus 0 times 2 over 9 plus 1 times 1 over 9 plus 2 times 3 over 9 plus 3 times 1 over 9. I'm sorry, 2 over 9. And we have, if we all sum it up, we will get 4 over 3. So that is expectation for x. For variance of x, we'll need to square the first x's numbers. So -1 squared times 1 over 9 plus 0, which is equal to 0 again, plus 1 squared times 1 over 9 plus 2 squared times 3 over 9 plus 3 squared times 2 over 9. And then we'll all subtract this with expectation of x squared. So we'll take this number right here and we'll square it. And we'll just subtract this. And we got a final estimate of 16 over 9.
Now I'm going to be explaining number 5 until 6b. So for number 5, every day Richard takes a flight between Aston and Beijing. On any day, the probability that the flight arrives early is 0.15, the probability that it arrives on time is 0.55, and the probability that it arrives late is 0.3. A. Find the probability that on each of the 3 randomly chosen days, Richard's flight does not arrive late. So we can write this as x is a binomial distribution with 3 trials, and the probability of success is 0.7, which is the probability that it arrives early plus the probability that it arrives on time, which is 0.15 plus 0.55. Hence, it will give us 0.7. As the question is saying that on all 3 of the days, the plane doesn't arrive late, then we can write the probability as 0.7 power 3, which is 0.343. B. Find the probability that for 9 randomly chosen days, Richard's flight arrives early at least 3 times. So in here, we can write x as a binomial distribution with 9 trials, and the probability of success, which is 0.15, as that's the probability that his flight arrives early. So as the question says at least 3 times, we can write it as the probability x is greater than or equals to 3. And that will be equals to the probability that it arrives early 3 times, plus 4 times, plus 5 times, plus 6 times, plus 7 times, plus 8 times, plus 9 times. Or we can also write it as 1 minus the probability that it arrives early 0 times, 1 times, plus 2 times. So here we can write 1 minus, and the probability that it arrives early 0 times, which is 9 choose 0, multiplied by 0.85 power 9, which is the probability that it doesn't arrive early, powered 9, as it doesn't arrive early all 9 days, plus the probability that it arrives early one of the days, which is 9 choose 1, plus 0.15, which is the probability that it arrives early, times 0.85 powered 8, which is because it doesn't arrive early 8 days. Then again, the probability that arrives early 2 days, which is 9 choose 2 multiplied by 0.15 part 2 multiplied by 0.85 part 7, as it arrives early 2 of the days and it doesn't arrive early 7 of the days. Then we would get 1 minus 0.8591, which will give us a final probability of 0.1409. For C, 60 days are chosen at random. Use an approximation to find the probability that Richard's flight arrives early at least 12 times. So here we can write again the binomial distribution, which has 60 trials, and the probability of success again is 0.15. In here, there are too many number of trials, hence we can use normal distribution to approximate the answer. So here, the normal distribution, the mean would be the number of trials multiplied by the probability of success, which is 60 multiplied by 0.15, giving us the mean of 9. And then to find the variance, we would multiply the number of trials with the probability of success, as well as the probability of failure, which is 60 times 0.15 times 0.85, which will give us a variation of 7.65. Now, the question asks us that his flight arrives early at least 12 times. So we can write it as the probability that x is greater than or equals to 12. Here we need to standardize the normal distribution, so we would get probability of z is greater than or equals to 11.5 minus 9 over square root of 7.65. Here for the approximation, we are using 11.5 as we can see here in this, the normal distribution graph. When x is greater than or equals to 12, the shaded area will be this, and it would be including the box. Hence, as you can see here, the value here would be 11.5. Hence, we would be using the approximation 11.5. So, to get the z, we will be doing 11.5 minus 9 over square root of 7.65, which is the standard deviation, giving us a value of 0.904. And then, because it's greater than, it would be the same as 1 minus probability z is less than 0.94, as you can see in this graph, as the probability that it's greater than 0.94 would be this small area over here, which is the same as 1 minus this greater area, which is z is less than 0.94. Hence, we would get 1 minus 0.8169, which is giving us the final probability 0.1831. Now for number 6a, find the total number of different arrangements of the 8 letters in the word tomorrow. The word tomorrow has 1 T, 3 O's, 1 M, 2 R's, and 1 W. Hence, from the 8 letters, we can get the total number of arrangements, which is 8 factorial. And then we divide it by 3 factorial, as there is 3 O's, which are the same, and also divided by 2 factorials, as there's 2 R's, which are also the same, and giving us the total number of different arrangements, which is 3,360. For number 6b, find the total number of different arrangements of the 8 letters in the word tomorrow that have an R at the beginning and an R at the end, and in which the 3 O's are not altogether. So first, we can write that we can put the R at the beginning and the R at the end. We can simply ignore this, as the different arrangements for this would be 2 factorial over 2 factorial, as the R's are the same, which would give us 1, hence it would be redundant. Then, we can draw the arrangement as such so that the remaining letters, aside from the O's, which are T, M, and W, all have spaces in between them. For this, there would be 2 different scenarios that could happen. One where all 3 O's are not together, one where 2 of the O's are together, and the other O is separated. Now for the first scenario, where all 3 O's are separated, we can first write the different arrangements for the 3 letters, which are T, M, and W. So that would be 3 factorial. Then we would multiply it with 4 combination 3, which, as we can see here, there's 4 different slots for the O's to go in, and there's 3 O's. Hence, 4 combination 3, as we're using combination as the O's are all the same and there would be no difference between them. And then now, for the second scenario, we would add that as well. So for the second scenario, again, we do the same thing, 3 factorial, which is the arrangement for T, M, and W. But then this time, we would be doing 4 permutation 2. Same like before, there's 4 slots for the units to go in. But this time, there are 2 different units. One is the 2 O's that are together, and one, the single separated O. As these are 2 different units that cannot be interchanged, we are using permutation. so it would be 4 permutation 2 as there are 2 different units. Hence, our final formula would be 3 factorial multiplied by 4 combination 3 plus 3 factorial multiplied by 4 permutation 2, giving us the final total number of different arrangements, which is 96.
And now moving on to number 6C. 4 letters are selected at random from the 8 letters of the word tomorrow. Find the probability that the selection contains at least one O and at least one R. That will be our condition for the probability that they're gonna find in this question. And for the number of letters, we have 1 T, 3 O's, 1 M, 2 R's, and also 1 W. We can find the total number of arrangements first. And for this one, we can use 8 combination 4. Why? Because there are 8 letters that we want to put into 4 sections or 4 slots, like this one. Now for the probability, it's gonna be the number of possible arrangements that have at least one O and one R over the total number of arrangements with it, which is 70. For the first possible arrangement, we have OR and 2 other slots. These 2 other slots can be filled with the 3 remaining letters. Since we need at least one O and one R, we're gonna exclude the O and R from the remaining letters, leaving T, M, and W. And the T, M, and W we can put in these empty slots. For the second possible arrangement, we have O, 2 R's, and 1 slot for the 3 remaining letters. For the third possible arrangement, we have 2 O's, 1 R, and 1 slot for the 3 other letters. For the 2 remaining possible arrangements, we don't have the slot for the 3 remaining letters. We're just gonna include the O and R. For the fourth one, we have 2 O's and 2 R's. For the fifth possible arrangement, we have 3 O's and 1 R. And to solve it, for example, for the first possible arrangement, we have 3 combination 1 multiplied by 2 combination 1 multiplied by 3 combination 2. And the reason why we use like for example this one, 3 combination 1, is because we have 3 O's that can be placed into one slot, and for the R, we have 2 R's that can be placed into one slot. And for the 3 combination 2, we have 3 of the remaining letters that can be placed into the 2 remaining slots. That goes the same for the rest of the possible arrangements, like this one, 3 choose 1 multiplied by 2 choose 1 multiplied by 3 choose 1. The 3 choose 1 is because we have 3 O's that can be placed into one slot. We have 2 R's that can be placed into 2 slots, and we have 3 remaining letters that can be placed into one slot. And after you multiply all of them, you add all of them up, which gives us the number of possible arrangements that has at least one O and one R. And after this, we just divide this value by 70, which will give us the probability of the 4 selected letters that contain at least one O and one R. And now moving on to number 7. For 7A, state an advantage of using a stem and leaf diagram compared to a box and whisker plot to illustrate this information. So first, why do we use a stem and leaf, and why do we use a box and whisker? A stem and leaf can show the shape of the data. Stem and leaves are typically made like this, and you have the values here. For example, it's this much, and for example, in this side there are this many data. And for example, you have group A and group B. these values, they show the shape of the data, and aside from that, they include all of the original numbers in the plot, in the diagram. And compared to a box and whisker plot, which are made like this, this shows the first line, this one shows the first quarter. There's also a line in the middle here that shows the second quarter or the median, and then there's the third line that shows the third quarter. And typically there are also two other lines here that show the other remaining data outside of the quarters. Now, but this doesn't exactly show all the data. For example, in between the first quarter and the second quarter, you don't exactly know all the values inside of this. However, for the stem and leaf, you get all of the values. You get all of the numbers, all the data here, and you can see them immediately. In the mark scheme, it says it includes all the data, and that's also what I put here. And now for number 7b. 7b says represent the data by drawing a back-to-back stem and leaf diagram with Amazons on the left-hand side of the diagram. Now for this one, you just need to draw a stem and leaf diagram. Now looking back at this, at the data that we've been given, for the Amazons we have 11. For both Amazons and Giants, we have 11 basketball players on each side. For the Amazons, we have basketball players with the heights 205, 198, 181, 182, 190, 215, 201, 178, 202, and 196 and 184. Now these aren't arranged in the order from lowest to highest yet, unlike the Giants, which have been ordered from 175, 182, 184, 187, 189, 192, 193, and 195, 195, 195, and 204. Now for this, usually a stem and leaf diagram also has their key, and from this, like what I've underlined here, we can use the first two digits of the 3-digit numbers for the middle here. For number 7b, represent the data by drawing a back-to-back stem and leaf diagram with Amazons on the left-hand side of the diagram. Here I've already drawn the back-to-back stem and leaf diagram, which shows the Amazons on the left-hand side and the Giants on the right-hand side. And for the key, for example, we have what should we use? For example, we have one. Okay, there we go. For example, we have 1, and 1, 8, and 3. This would mean that the Amazons so it would mean that the Amazons have someone with the height of 181 centimeters, while the Giants have someone with the height of 183 centimeters. And as I've explained before in number 7a, the stem and leaf diagram shows all of the original data from from the data given in the table above, and which is why that is better than a box and whisker plot to illustrate this information specifically. And now moving on to 7C, sorry, which is finding the interquartile range of the heights of the players in the Amazons. So to find the IQR, we just need to subtract the third quartile with the first quartile. Why do we do this? We do this because to find the scope of the data. For example, the third quartile of the Amazons lie in 202, which is just here. And how do we find this? For me, I use this method. So for example, the Giants have 11 basketball players, right? And you just need to 11 plus 1, which equates to 12, and you just divide the 12 by 2, which equates to 6. And then we just need to find the sixth data from this Stammenlich diagram. So 5, 2, 4, 7, 9, and 2. This means that the median of the second quartile of the Giants is 192 centimeters. So what is the first quartile and the third quartile? In the first quartile, we just need to look at the remaining numbers on the first side before the median. We have 5, 2, 4, 7, and 9. We can use this method again. So that will be 5 plus 1, because we have 5. If we count this, we have 5, 2, 4, 7, 9. 5 plus 1 equals to 6. 6 divided by 2 equals to 3. So we just need to search for the third number, which is 4. This means that the first quartile of the Giants is 184, and for the third quartile, we just need to look at the second half of the data under the median. And following this again, the third data would be this. And that means the third quartile of the Giants will be 195. And that's for the Giants. That's for the example. So now let's try to look for the first quartile of the Amazons. Following that pattern, 1, 2, 3, 4, 5, 6, 196, and the third, 182. And from this, we can establish that the first quartile is 182 centimeters, while the third quartile is 202 centimeters. And like I said before, how to find the interquartile range is by subtracting the third quartile by the first quartile. And so we get 202 minus 182, which equates to 20 centimeters. And that will be our interquartile range for the Amazons. And now let's move on to 7D. In 7D, for new players join the Amazons, the mean height of the 15 players, now 15 players, in the Amazons is now 191.2 centimeters. The heights of 3 of the new players are 180, 185, and 190. Find the height of the 4th new player. So for 7D, we just need to find the height of the 4th new player. And from what we can get here, the mean height of the 15 players is now 192, and that is 4 players. Wait, sorry. That is 4 players more than the original count, which is 11. 4. And these 4 new players include the ones that have 180, 185, and 190. But we have one missing, and that is who we want to find. So how do we get this? We know that the mean is now 191.2 for the new one, which is 15. And we can also find the one for the 11 players from the data above. So to find the total sum of the 11 players, we just need to do sigma 1 and no, sigma 11, which are all the heights added up together, which equates to 2,132. And then we just need to find the sum of the 15 players, and to find this we just need to multiply the mean, the new mean, with the number of players. This is because usually when you want to find the mean, for example, this is the mean. We usually do sigma n over n, which is why we're reversing it. So so it becomes mean multiplied by n equals sigma n. And we know that sigma 15 equals to sigma 11 plus 180 plus 185 plus 190 plus the height of the 4th player. And from this we can solve it by subtracting 2,868, which is the sum of the new 15 players, by 2,132, which is the sum of the 11 players, 180, 185, and 190 to get the height of the 4th player, which is 181 centimeters. And that is all for this section of the video.
That's all for our video today. Thank you all for watching, and don't forget to like, subscribe, and turn on notifications on Turn Youngman's YouTube channel, and also comment down below if this video was helpful or not. Thank you!